Okay, so good morning, everyone. Thanks for coming at this early hour. What I'm going to discuss is just some future challenges of modeling THMC systems. And as you're probably already aware, the thermal, hydraulic, mechanical, chemical systems are extremely difficult to model because of the vast range of interactions and timescales. And there's a lot of models out there, but there's not enough models, or very few, that allow for the nucleation, growth, and coalescence of fluid-fluid fractures that respond and grow to the regional stress field and the perturbations in the stress field due to the evolving crack network. So in my view, the biggest challenge is to develop computationally fast, high-resolution THMC models in 3D. Now, what is needed are realistic models of fracture development and interactions. And as a bonus, you get mechanistic models of seismic hazard assessment, realistic flow models, heat transport, and chemistry. And ideally, if people want to use this, you also want to have an interface that's easy to use to set up the system, intuitive pre-processing, and interactive and very cool scientific post-processing, all linked together. Now, we've all seen this before. Everything is coupled to everything else. And in terms of the physics, what we need are mechanics, the elasticity, plasticity, hardening and softening, damage models. For the hydraulics, we need single-phase and multi-phase flow, heat transport, local thermal equilibrium, non-local. Chemistry is transport of the constituents, chemical erosion, phase transitions. So basically the entire range of everything you can think of. And all of them need to be coupled. So I want to step back now and just show how far you can get with the simplest of models to try to determine what is the most dominant thing that controls these systems. So if you develop a very simple model for the Basel fluid injection experiment, where you have a simple Moore Coulomb failure condition, you have a pressure-dependent permeability, so it's a nonlinear diffusion problem. You put some distribution of incipient faults within a regional stress field with some probability distribution that they're optimally oriented. And the main point is that you allow for a large increase in permeability at the onset of slip. So you increase it by 2.5 to 3 orders of magnitude. So with such a simple model, you take a look at the Basel fluid injection experiment, and the hypocenter is sort of aligned northwest-southeast, and in depth view, you see here it's this is the way it fanned out, so you can assume it's a two-dimensional problem in this plane. You have a nonlinear permeability, where the permeability is a function of the effective normal stress, and basically you just solve a nonlinear diffusion equation. So that's all this model is. It's ridiculously simple, but it just solves the nonlinear diffusion equation. And so what happens is that at the, this would be the state of stress within the model. As you pump up fluid pressure, each one of these blue points crosses the failure curve, and at that, when it hits the failure curve, you increase its local permeability by about a factor of 1,000. And we see how far we can get with such a model. So here's the input. It's got an initial permeability distribution because the virtual fault planes are oriented at some angle relative to the regional stress. And you input this pressure time history here at about 4.8 kilometers. And what happens? The permeability field grows in response to the injection of the fluid pressure. Now, if you look at the average permeability of the stimulated region, what you see here is it started here around 10 to the minus 17. It peaked at around 10 to the minus 14.5, and Basel was measured about here. Now, Thomas would claim that it's all prescribed, but we have an argument about that. But in any case, the average permeability, which is what you want to know in these systems, matches quite well what was measured. Now, if you look at the evolution of fluid pressure in the system compared to the squares here, which are the measured hypocenters, you see here that it captures quite well the migration of the hypocenters from that point. Here's the input, this is the output, here's the rate of earthquakes. Blue is what was measured, and red is what was modeled. So you see here, even after they shut the system down due to an unexpected earthquake, you still get earthquakes after shutdown because you've left behind this high pressure bubble within your system that continues to diffuse and trigger earthquakes along the flow path. So if you look at the black dots, which are the model, and the red dots are the measured hypocenters as you go in the x direction or in the z direction, you see it's a very good match between model and observations. I won't get into the details here, but you can also get quite a good match with the flow rates, both in and out, and get some estimation of the average permeability of your stimulated region here, because this is just Darcy flow across the cylindrical cross-sectional area and the pressure gradient. And when you shut down, you get your flow reduction because you have the same average permeability field, but what's happening here now is you have the minimum principal stress squeezing shut your system and acting in a Darcy flow type way. So this is a very good match. And the fact that such a simple model reproduces all of the observations at Basel says that, okay, it's simple, it's wrong, but it gives you some insight, and it shows that the system is dominated by very large changes in permeability over very short time scales. So this is the kind of thing that's going to need to be modeled in more sophisticated models. So therefore, models must explicitly include the evolving fracture networks that control THMC systems. Now, the approach that we're taking is to basically start from scratch and reformulate the governing equations in explicit finite difference scheme written in CUDA and set up for the graphics processing unit type cluster. So these are some results from a pore-elastic-plastic model with nonlinear diffusion in GPU. The advantage of GPU is that you can get higher resolution, faster computational times than you have with normal problems where you have to invert the large matrices. So the first step, of course, is to start to compare to laboratory data. So this is some experiments that were done in Potsdam where they had a fluid pressure boundary here on a pre-stress sample, and this is the simulated result, the evolution of the fractures in response to this diffusing front. Another experiment was they injected straight into a borehole here, and you see here as you inject fluid pressure into the borehole, the evolving crack network with the same angles as what is observed. The interesting thing about this is that this was simulated at the resolution of the grain scale of the experiment, and it was like 2 hours on one laptop with one GPU card. So there's a very big advantage if you can optimize for the GPU. Now, we've been developing, Thomas Heinze and us have been developing more sophisticated models to match with laboratory data. Now we've included hardening, weakening, and damage. So this is the experimental result. These are the this is the numerical result with the stress strain curve. The red is the simulation, and the black dots are the experiment. And here with inelastic axial strain, same thing, very good match. So hardening, weakening, and damage have now been developed. We've been trying, because you always run into problems, but we've been trying different strategies, for example, with mesh-free methods of an elastic-plastic rheology. And here is some results using mesh-free methods in compression and extension. And it's an elastic-plastic rheology, so here's the comparison of the model versus the data. It looks very good. Mesh-free methods still have potential, but they do get kind of heavy, so we're just discovering this as we go. So now we've got hyperplasticity to get the full hysteresis loop of load, unload, load, unload, unload. So that's including hardening, weakening, and damage with a multidimensional yield function. And looks very good here between simulation and experiments. So we're making more and more complicated rheological models to capture what really happens in post-failure behavior. Here, and as always, you compare to experiments. So here's axial stress versus axial strain. Axial stress versus axial strain. Here you get this dilatancy here at the onset of failure. Now, once you have these models, you can bump up your scale to take a look at some real systems here. This is the Bohemian earthquake swarms, and this is these. So this is the last swarm in 2010, and you can model it by a simple single plane here. So this is driven by CO2 injection from some mantle source, so it's very similar to EGS systems. This is the fracture network evolved by compressing the system over some large amount of time, and then you inject the CO2 through the system. We have a scheme, don't want to get into details, but the important part of this thing is to estimate numerical earthquakes. And so here we use the deviatoric strain rate when that kicks up as the start of an event, and if it happens during some excitation time, we add it all up together into one event. Excuse me. And you can make comparisons once you have a good model with a time scale and a length scale. There's a comparison. The simulation are the black dots, and the green are the observations. Here you can compare the magnitudes, and this is very important because what you want to do is be able to estimate mechanistically what is the maximum magnitude you can expect in some sort of injection scenario. And you get good Gutenberg-Richter magnitude frequency statistics. So now we're trying to put everything into 3D. This is the plastic-elastic-plastic model in 3D, and we're looking at different strategies, explicit finite differences. We're looking to try to get some implicit methods going on the GPU. The GPU technology has improved quite well. Here's an example of a crack network evolved in 2048 by 2048 on 4 GPUs, so the 4 different in a GPU cluster here. Very high resolution. Crack network, we've got some boundary condition issues here going on that we're trying to work on here. But this is the kind of resolution that we expect to get when we get full going here. You would have this crack network, you would go down numerical crack network, you can inject a fluid pressure field in here and new cracks would evolve in response to the thermoelastic, pore-elastic, plastic excitation. So this is our goal here, is to put all of this stuff into a huge GPU cluster here, pore-elastic-plastic rheology, nonlinear diffusion, hardening, softening, and damage, fluid rock coupling and heat transfer. We wanted it all in 3D, two-phase, thermoelasticity, saturated, unsaturated, equation state for CO2, reactive transport, anything else you want to throw in here. We've established the system so that it's very modular in approach, but our philosophy is that you need to start with M. If you get M right, that's the most important thing because it controls the ultimate thermohydraulic and chemical behavior of these systems. So we are taking the approach to first master the mechanics, customize for evolving modern architectures, for example, GPU or many integrated cores. We are making substantial progress and technical barriers remain that we are currently dismantling. So thank you for your attention. And that's it. And please speak up. I don't hear very well.
Hello. At the permeability test, it's expressed in terms of sigma bar. What was exactly the sigma bar?
It's the effective normal stress. Okay. Yeah. So basically, if you have a high normal stress, you have low permeability, and if you it's a proxy for the aperture.
I thought it was kind of average.
No. It's the effective normal stress. Sorry about that. Yeah.
But probably did you try any other kind of relation between permeability? Because you actually have an exponential like permeability depending on effective stress, and it might be that it's not actually the case in all the systems. So have you ever tried to implement new kind of equation for the permeability dependence?
Yeah, we are because we calculate now when we have the mechanics the effective plastic strain. We want to put a effective plastic strain as a proxy for the permeability. So we can try different things. But so far I've gotten pretty good results with this exponential.
Okay. Yeah. Are there any other questions from you? I may have just another question. You just looking at your final conclusion, you talked about technical barriers. So what are those technical barriers that you are?
Yeah, the dismantling technical barriers. Yeah. Well, there are some technical problems that you come across when, and that is the GPU. At least the first generation of them hated to invert any sort of matrix. They're very good at explicit finite difference because you just march forward in time and very quickly. But they don't like to invert, so all implicit methods sort of go out the window. The latest GPU cards are much more amenable to inverting matrices, so we need to, we're looking at different numerical algorithms, finite elements or implicit finite difference, because you can't go very far, or you run into troubles with all explicit finite difference when you're getting all of the mechanics in there. So yeah, there's some technical barriers, but we're open to solve them.
No other question, then thanks a lot.
Thank you.